here. All right, so section 10.1, power series, definition of an infinite series. A couple of things we need to be comfortable with. An infinite series is an expression of the form a sub 1 plus a sub 2 plus a sub 3. We've talked about sequences already, and sequences are just a list of values separated by commas. But a series is the sum of all of those terms. We could have addition and subtraction, but there is addition or subtraction going on between each of the terms. So we need to remind ourselves about summation notation or sigma notation, called either. Did you guys talk about this at the beginning of the year? A little? A little bit? Okay, or in previous classes, maybe in pre-calc. Yeah, okay. All right, so this means, the sigma means the sum of the series a sub k, defined by a sub k, from k equals 1 to k equals infinity. What this means is that you will plug your k value into whatever your definition of the series is. So if you want to get a sub 1, you plug 1 in for k and get the value. Plus, then when k is 2, you plug 2 into the definition, and so on, to get all of your terms. And each item in the series is called a term. And a sub n is referred to as the nth term. Okay? We will be determining if a given series converges or diverges, just like we did with sequences, but it's done in a little bit different way. And if a series converges, it means that it adds to a particular sum. It reaches a number. If it diverges, it means that it's always adding more and more and more. Okay? Same stuff as with sequences. So, if we want to figure out if an infinite series converges, we have to use what are called the partial sums. So this is from your text. The partial sums of a series form a sequence. All right, so we need to understand what partial sums are. Partial sums are some portion of the infinite series. So s sub 1 would mean the sum of the first term. So if we use this series that we have in our box, what is the first term? It is a sub 1, so s sub 1 would be a sub 1. S sub 2 would be the sum of the first two terms. A sub 1 plus a sub 2. These are called finite sums because they stop. They don't continue on forever. S sub 3, obviously a sub 1 plus a sub 2 plus a sub 3. And s sub n would be a sub 1 plus a sub 2, continuing up to a sub n. All right, so if we want to determine if this series converges, then we will create what is called a sequence of partial sums. And that sequence would be s sub 1, comma, s sub 2, comma, s sub 3, s sub 3, on up. Okay? And this sequence is where we tie into the last chapter, where we found out if sequences converge or diverge. So if the sequence of partial sums as n approaches infinity of s sub n, if that sequence equals a number, then the series converges to that number. Okay, and if our limit as n approaches infinity of that sequence equals positive infinity or negative infinity, or it oscillates, or any of those situations where we found divergence in the last chapter, then the series diverges. Okay? So that's the basic rule for determining if an infinite series converges or diverges. All right, so let's do a couple of examples. The first one, we are looking at the series 1 minus 1 plus 1 minus 1 plus 1 and so on, and we want to know if it converges. So the first thing we must do is make our sequence of partial sums. So don't look at it and try and decide just by gazing at it. We have a process we can follow. We'll make our sequence of partial sums. So S of 1 would be the sum of the first terms, which would be what? 1. S of 2 is the sum of the first two. 1 minus 1, which would equal 0. S of 3, 1 minus 1 plus 1. And S of 4, I usually go out to about 4 terms. Minus 1 plus 1 minus 1. So our sequence of partial sums would be 1, comma, 0, comma 1, comma 0, and it would continue. Tell me about the limit as n goes to infinity of our sequence. It does not exist because of oscillation. This is oscillating. So, because there is no limit, our series would do what? Diverges. Okay? All right, let's try one more. On this one, does the series 3 tenths plus 3 100ths plus 3 1,000ths and so on converge? So let's make our sequence of partial sums. S of 1, and on this one it might be easier to see with decimal. Not always the case, but we'll look this time. We get 0.3. S of 2 would be 0.3 plus 0.03, giving us 0.33. S of 3 would be what? 0.3 plus 0.03 plus 0.003, giving us 0.333. All right. So our sequence of partial sums is 0.3, 0.33, 0.333, and so on. Think about the limit as n goes to infinity of our S of n. What would it equal? 1/3. So we'll get 0.3 repeating, which we recognize to be 1/3. So the series converges to 1/3. Okay? All right. Oh, I'm sorry. Yeah. Yes. Now, we will deal with a lot of different series, and quite often it's difficult to find the actual sum of a series. This one does converge to a value of 1/3, and this is a specific type of series called the geometric series. That's one of the very few that we can actually find the true sum of. So if you are asked on an AP exam to find the sum, Connor, stay with me here, Connor. Thank you. It's a thrilling day in here, thrilling. All right, so if you were asked to find a sum on the AP test, then what should go off in your head is it's probably geometric. And then you can apply all our little rules for geometric series. Okay, so it's one of those things you want to look for. Let's take a look at our next piece of information. All right, so this tends to be a confusing idea, but it's a very nice and powerful tool to determine if the series you're looking at diverges. It's a quick way to tell. It's called the nth term test. And in this chapter, your book doesn't reference it that way, but that's what it is, and that's what you'll hear me calling it. And this test does not prove convergence. We do not use it to tell us if the series converges, but it can tell us if the series diverges. So, I would, if I were you, you can read what's in the box, but I would not put what's in the box in your notes. I would put this in your notes. So this says, what's in the box says, if the infinite series that you're given converges, if we know it converges, then the limit of its definition will go to 0. Okay? So, if we have a convergent series, its limit will go to 0. This is not saying that if the limit goes to 0, it will converge. Everyone clear on that? Okay. So the meaningful part and the useful part of this idea is that if the limit as k goes to infinity of our definition, notice there's no sigma here, it's just the definition of our series, if that does not equal 0, then the series diverges. And the reason is, a to k is what we use to figure out each term that we're adding. So if k gets huge, if our a to k is getting bigger, not going to 0, then we're adding bigger values each time. And our sum is going to inflate. Okay? But if this limit does go to 0, we can draw no conclusions. We can't say that it converges, we can't say that it diverges. Okay? So on this one, if we try this, we have the limit as k approaches infinity of 2 to the k. What will that approach? Infinity, right? That'll get huge, which does not equal 0. So what can we say about this series? Series diverges. Down here, when we look at this one, the limit as k approaches infinity of 1 over k, what does that equal? That one equals 0. No conclusions can be drawn. Because there are a lot of series whose definition will go to 0, but the series still does not converge. Okay? Alright, so it's called the nth term test, very useful for determining divergence. I would love to have this year be my first year ever where no one tells me that a series converges by the nth term test. That would be very exciting for me. We cannot use it to determine convergence. Alright, so our last type of series that we need to talk about today is the geometric series. It's one of the first ones that we deal with because it is so easy to work with, and we already know what a geometric sequence is. It has a common ratio. Well, so does a geometric series. Each term, we get the next term by multiplying by that common ratio of r. Okay? So the standard sigma notation for geometric series is the sum from n equals 1 to infinity of our first term, which we just call a, times r to the n minus 1. There's our definition. And think about this. If our ratio is bigger than 1, and so to get each next term, we're multiplying by something bigger than 1, is my series going to converge or diverge? So to get the next term, we multiply by 5, let's say. It's going to what? Diverge, because each time I'm taking some value, I'm going to multiply it by 5 to get the next value. That's going to make my sum larger, right? And that's going to keep going. So, if r, our absolute value of r, is greater than or equal to 1, the series will diverge. But as Andrew just said, if it's a decimal, or if it is less than 1, let's say, then we're multiplying by a fraction, and what we're adding each time is getting smaller and smaller and smaller and smaller. And so, our series will converge. If the series converges, as I said, geometric series is one of the only ones that we can actually find the sum. The infinite sum, which we'll call S, will be A over 1 minus R. Very easy to work with. Questions?
On a data versus
Oh, no, sorry. Yep, thank you. I don't want to do not want an equals here. Thanks very much. Thank you. I do not want that. All right. So there is our rule for finding the actual sum. So now let's go through and look at these examples and use this information to help us get through them. All right. In A, they're giving us sigma notation from n equals 1 to infinity of 3 times 1/2 to the n minus 1. Now, we'll get better at recognizing that as geometric, but through all of the series chapter, it's easiest, I think, if you write out the first 3 or 4 terms. So what is my first term? That means I plug 1 in for n, and what do I get? I get 3. I get 0 for the exponent, so I get 3 plus, plug 2 in for n, 3/2, plus 3/4, plus 3/8, and so on. All right? So looking at that, what's my common ratio? What am I multiplying by each time? 1/2. Absolute value of r is less than 1. So my series converges. And now let's find out what it converges to. S is going to be my first term, which is 3, over 1 minus the r, which is 1/2. 3 over 1/2 gives us 6. So our sum is 6. All right, in part B, they give us the series written out term by term. So now let's write the sigma notation, because we need to be able to go back and forth with these. So how would you like to write this? The sum of, what's my first term? 1 times negative 1/2, correct? To the n minus 1 from n equals 1 to infinity. What's my common ratio? Negative 1/2. Absolute value of that is less than 1. So the series converges. And then quickly in our formula we get s equals 1 over 1 minus negative 1/2 to give us 2/3. And we would say the series converges to 2/3. All right, let's try the next one. This one is 3/5 to the k. And it starts at n equals 0. So this is another way that you can write, oh dear, the a geometric from n equals 0 instead of 1 to infinity of 3/5 to the n. Let's write out the first few terms. What's the first one? Nope. What is it? 1 plus 3/5 plus 9/25 plus 27 1/25. All right. My common ratio here, 3/5. That's a 5, not a 3. And our sum would equal 1 over 1 minus 3/5, or what? 5/2. Okay, so the series converges to 5/2. All right, the final one, I think they give us term by term. Yep. We have pi/2 plus pi squared fourth plus pi cubed over 8, and so on. Help me with the sigma notation. N equals 1 to infinity of pi over 2 to the what? Would it be n minus 1? Take a look. If you plug in So it'll just be n, right? Make sure it matches up so you get the first term correct. So pi halves to the first is our first term. All right, what's my common ratio here? Pi halves. How does that relate to 1? Is greater than 1, so the series diverges. All right, that's all we've got for the first section, for our first day on the first section. So your homework is 1 through 20, and you have a good bit of time. And these are not that hard. So get started, books open, get some problems done. If you're not using your time, I will assign more.